Great! So now I have shown you on paper all of the steps on how to do Gaussian elimination. So in principle I could leave it here and you would be on your own. But I know from experience that these are very difficult lectures to follow without having an actual example from start to finish, which is what I'm going to do now. Okay, so let's do a complete example showing all of the steps. So, example, solve the following system of equations. So let's remember what the steps were. We start with the system of equations. We write it as a system of matrix times vector equals vector. We put it into an augmented matrix form. Then we do Gaussian steps. And we arrive at row echelon form. And then we solve x. Okay, those are the steps. So let's do them. So first we start with the system of equations. So our system of equations, I'm going to rewrite it here, but I'm going to line up the variables so that it's easier to see. So the first equation is 1 times x1 plus 1 times x2 plus 1 times x3 plus 1 times x4 equals 7. The next equation is 1x1 plus 1x2 plus 0x3 plus 2x4 equals 5. Okay, I added a 0 so that the x3s are nicely lined up. Yeah. Next equation is 2x1 plus 2x2 plus 3x3 plus 1x4 equals 16. So that's my system of equations. And now it's very easy to identify the coefficients, which are all of these. Yeah. And the independent coefficients, which are these three. So we can write them in matrix vector multiplication form. So this will be a matrix given by 1, 1, 1, 1, 1, 1, 0, 2, 2, 2, 3, 1. This will be matrix A. This is multiplying a vector which is x1, x2, x3, x4, which are our variables, and this is equal to the independent coefficients, which are 7, 5, 16. So now the system is written in A times x equals b. Okay? So we are here. So next we write it as an augmented matrix, and this is simply writing it wasting fewer ink. Yeah. So we basically write the matrix here. And then we add a vertical line and we write the independent coefficients. So now we are in this step here. Very good. So of course I did the steps explicitly, but in practice it's perfectly fine if starting from this you directly write this. Okay, I would recommend doing that so you don't waste time with the previous steps. But I just wanted to make sure that you understood them. That's why I did them explicitly. Okay, so now we are here. Now the next thing we need to do is to perform Gaussian steps to bring this augmented matrix into row echelon form. Okay, so let's start. So first of all, what are the pivots here? So the pivot is the first non-zero number in each row. So we have a pivot here, a pivot here, and a pivot here. So this is not in row echelon form because these pivots should be to the right of the pivots above. Yeah. So we want zeros to appear there. We don't want those to be pivots. Therefore, we do Gaussian steps. And remember, the Gaussian steps are aimed at producing a zero in these places. So the trick is to get the row where you want the zero to appear and to subtract the ratio of the pivot above to the number that you want to make zero. In this case, that's 1. Okay, so you just say subtract 1 times the first row. Okay, So my recommendation is always to use the pivot row to create the zero. Although it doesn't matter, you could use any other row, but you will always have a correct way of doing it if you just do it with the row that you want to keep the pivot. So if you always subtract the row in which you already have the pivot you want to keep. That's how computers would do it, okay? So if you wanted to actually code Gaussian elimination, which would be a great exercise, by the way, you can always do it in the same way. Yeah? You just have to subtract the ratio of the two numbers times the first row. Okay, so that result, you put it into row 2. So what do you end up with? First, copy the first row. And now we do the second row, minus the first row. So 1 minus 1 is 0, 1 minus 1 is 0, 0 minus 1 is minus 1, 2 minus 1 is 1, 5 minus 7 is minus 2. Next, we are dealing with the third row, yeah? So therefore, we want to have a 0 here. So we start with the row we want the 0 to be in, and we subtract the ratio of the pivot we want to keep with the number that we want to be 0, yeah? So the ratio of 1 and 2 is 2. So we subtract twice the row 1. And this will ensure there will be a 0 here. And the result, we place it into row 2. Okay, so 2 minus 2 is 0, 2 minus 2 is 0, 3 minus 2 is 1, 1 minus 2 is minus 1, and 16 minus 14 is 2. Great. So those are our first two Gaussian steps. So now we are here. So where are the pivots now? So the first row, the first non-zero number is this pivot. Perfect. In the second row, the first non-zero number is this one. And in the third row, the first non-zero number is this one. So this is not in row echelon form because this pivot should be to the right of the pivot above. So we want this to be a 0. We don't want it to be a pivot. Yeah. So therefore, we are going to do the Gaussian step as always. So we get the row where we want the 0 to be, which is row 3. And we subtract the ratio of the two rows, which in this case is minus 1. So we subtract minus 1, so it's plus 1 times row 2. The row. So basically, we are using this pivot to make sure that this becomes a 0. Yeah. So if we do that, we are basically adding row 3 plus row 2. And the result, we are going to put it into row 3. So what do we end up with? First, let's copy the rows above. And now we do this. We do row 3 plus row 2. Since we know we will have zeros over here, we don't have to compute those. So those will be 0 minus 0 plus 0, 0 plus 0. So that's easy. And the first time, and now we do 1 minus 1 is 0. And minus 1 plus 1 is 0. And 2 minus 2 is 0. Okay. So now we arrived here. Is this in row echelon form? Yes, it is. But let's check it. What are the pivots in each row? So the first row has this pivot. The second row has this pivot. And the third row has no pivots because it's all zeros. Okay? So every pivot is to the right of the pivots above, and therefore we are in row echelon form, and we can do this staircase pattern. Yes? So we arrived here. Yeah? So we are only left with the last step, which is to solve for x. And remember, in this last step, I gave you 3 possibilities. Unique solution when there are as many pivots as columns. No solution when there is a row at the bottom which says 0 equals k. Or infinite solutions, which is when some columns do not have pivots, but all the rows below are 0 equals 0. So there is no 0 equal k row. So in this case, we are in this third case. So we have infinite solutions, okay? Why is that? Because we have two columns that do not have pivot. Yeah? Those two columns don't have a pivot. Remember, each column is associated with a variable. Yeah. And the first step in this case 3 is columns that don't have pivot correspond to variables that are free variables. So our first step is exactly that. We say that x2 equals alpha and x4 equals beta. It's very typical to use Greek numbers for free variables or free parameters. This will be our sliders, if you remember chapter 1, equations of lines and planes. Okay, so we start by knowing that these two variables are free variables because their corresponding columns do not have a pivot. Yeah. So next we solve the system by inverse substitution. So row 3 is just telling us that 0 equals 0, so there's nothing we need to worry about. Row 2 is telling us that minus x3 plus 1x4, which is beta, equals minus 2. Therefore, we can say that x3 equals 2 plus beta. Okay? Now we move to row 1. And row 1 is telling us that 1x1 plus 1x2, which is alpha, plus 1x3, which is 2 plus beta, plus 1x4, which is beta, equals 7. Yes? So I'm basically converted this into the corresponding equation and substituted the known values of x2, x3, and x4. So now we can solve this equation for x1, and we obtain that x1 equals, so 7 minus 2, that's 5, and then we do minus alpha minus 2 beta. Okay, so we have arrived at solutions for every single variable. So that would have solved the problem, but it's nice to put it into a parametric form, into a vector parametric form. Okay, so how would we do it? Okay, let's write all the solutions. x1, x2, x3, and x4. Put it as a vector. This is equal to, so x1 is 5 minus alpha minus 2 beta. x2 is equal to alpha. x3 is equal to 2 plus beta. And x4 is equal to beta. Notice that I aligned the terms because now I'm going to do the following. I'm going to write a vector with the independent terms that don't involve alpha or beta. So that would be this. It would be 5, 0, 2, 0. Then plus, and all the terms that multiply alpha, which will be minus 1, 1, 0, and 0. And then plus beta times all the terms that multiply beta, which will be minus 2, 0, 1, and 1. And this is equal to our x solution, which has two free parameters, or two sliders, alpha and beta. Okay? And this is a beautiful way of writing the solution to this system. Why is it beautiful? Because it is the equation of a plane in 4-dimensional space. Okay, so notice how nice this was. We had 3 equations and 4 unknowns, and we had to solve this. Yeah, and what we arrived is that we wrote this as a linear system of equations in which we have an input vector x, which was unknown and which was a 4-dimensional vector. And we know that by applying this linear transformation A, which represents the system, we arrived at this vector b, which is known and which is 3-dimensional, which is this vector b here. Yeah. So we knew the transformation and we knew the vector b. So we had to find this vector x, which is a 4-dimensional vector, which after applying this transformation leads to b. And we did it perfectly by following Gaussian elimination. So we write the augmented matrix, we do Gaussian steps to get all the pivots arranged in the correct way, and then we solve for x using this algorithm that all the columns without a pivot are free variables, and then the rest of the variables can be solved by inverse substitution, starting at the last row and moving up. And then it's very elegant to write the solution as this format, parametric equation of a plane. So this is a plane in 4 dimensions. You cannot imagine it visually, but it's very intuitive. So the solution to this equation has 2 degrees of freedom, and there are infinite solutions. Yeah, it's any vector in this plane will be a solution to this system. Also, let's go even forward. Remember that I told you that the solutions to a linear system of equations could always be written as a particular solution, x0, plus the null space of A. Yeah, I told you that. So indeed, that's what happened here. So all of this is the null space of matrix A. Okay, and this is a particular solution. So if you substitute these values, 5, 0, 2, 0, into x1, x2, x3, and x4, you would solve this system. So that's one of the possible solutions. But then you need to add all of this infinite plane, which is the null space of A. Okay? Very good. So I think with a couple more examples, you are ready to master Gaussian elimination and do lots of problems to get used to it. Thanks for watching.